we have a cubic trigonometric equation tonight. And evaluate means to find the value. Some people will say, what is sine theta plus cosine theta? I like to use the expression evaluate. It means to give this thing a value. Now, the approach here, in my opinion, is not to try to find theta. The only way I would know how to find theta would be to use like Newton's method or some numerical method. I have no idea how to get theta algebraically isolated. Perhaps there's some trig identities or whatever, but there's another way to do this that just involves fairly rudimentary algebra. So let's take a look here. This sine cubed theta plus cosine cubed is just in this usual form for the sum of two cubes, okay? So a cubed plus, let's call that b. A cubed plus b cubed. Okay, very well known, easy. You can just multiply that out to verify that a cubed plus b cubed, the sum of two cubes, is a plus b. Okay, and then times a squared minus ab, the quantity, plus b squared. Again, a lot of you guys could have done without me writing that down. But anyway, that's a very well known, the sum of two cubes and the difference of two cubes has a similar appearance. Okay, so that's all we did. Now, why do we do that? Well, because you see we got what we're looking for right here. We are looking for the value of sine theta plus cosine theta. And again, we're not attempting to solve for theta. As far as I know, that's about impossible, really, you know, and again, unless you do it numerically. Now, another very fortunate thing happens for us right here. There's this unit circle identity here. Sine squared theta, I'll just write s squared plus c squared is equal to 1. If you think of a point spinning around on a unit circle with angle theta, this is just that formula, unit circle. Okay, it's in Cartesian coordinates, it's x squared plus y squared is equal to 0, but the y coordinate is actually the sine, and the x coordinate is the cosine. Okay, so in any event, you can see where this 1 came from. Okay, you can see where this 1 came from, and we're just left with minus sine theta cosine theta. Now, I got kind of stumped here, but it turns out it's a good idea to do a substitution here once you observe that a squared, okay, is equal to 1 plus 2 sine theta. 1 plus 2 sine theta cosine theta. Once again, you have cosine squared plus sine squared is equal to 1. Okay. Now, when you isolate sine theta cosine theta, you actually get this a squared minus 1 over 2. So we're trying to get everything in terms of a, and we'll end up with a cubic in a, and then we'll try to solve for a, and we'll try to determine which values of a could actually be equal to sine theta plus cosine theta. All right, so you can see that the original equation becomes this. Now, y'all, again, right up here, this part's a, right here, right? The a you see right here is the a that you see right here. And then this 1 that you see right here is this 1 you see right here. And we've just learned that a squared minus 1 over 2 is equal to sine theta cosine theta, right? And so when you do all of that, here's what you end up with here, folks, right here. Okay? Now, so we do know that sine cubed theta plus cosine cubed theta is equal to this in terms of a, all right? And the rest of this is just coming back up here and doing the 91 over 125, which is what I've done right here. Now, again, I'll omit some of the details here. There's just some collecting like terms, etc. And then getting a polynomial, a cubic polynomial in the variable a. Okay, in the variable a, again, and a is what we are looking for, right? It's just easier to write that down than to carry around sine theta plus cosine theta all the way through the problem. Okay, so there we go. Now, folks, notice here that, let's see here, you can, well, let's just come down a little bit. You can observe that 182 is equal to 2 times 7 times 13, and again, 125 is just 5 cubed. Now, there's a result called the rational zero theorem that says possible rational zeros are any combination of the divisors of 182 over any combination of the divisors of 125. So, for example, numbers like 2, 5. Again, 2 is a divisor of 182. 7 is the 2 times 7 times 13 is 182. That's the prime factorization. So possibilities would be 2 over 5, 7 over 5, 13 over 5. And y'all, technically, I should be putting plus or minuses in front of these numbers. 13 over 5. Okay. And also, nothing special about 5. You could also consider 2 over 25. And I'm not going to write them all down, but I just want you to know that the rational zero theorem is what we're going to use as a tool right here. 7 over 25. Right, and then 13 over 25. And this isn't a complete list, but I'm just giving you an idea of how the rational zero theorem works. The numerator is comprised of divisors of the constant term. The denominator is comprised divisors of the leading coefficient. All right, so here's what we got. All right. Now, y'all, again, it's boring to go through all this, but just a little bit of number sense. If you look at the size of the numbers, it turns out that 7/5 was the try that got it done. Okay. Now I did the synthetic division. You guys may have seen this. 7/5 is what got it done. And notice when you do the synthetic division, you see we get the 0 here, which means this is the same thing as doing long division. This is a remainder of 0. So that tells you that a minus 7/5 is a factor. Okay. If 7/5 is a 0, then a minus 7/5 must be a factor with an unknown quadratic. Now that quadratic is given to us, this Q of A is given to us by these numbers here, which constitute the coefficients of the quotient. All right. Again, you can do long division if you want. Notice I went ahead and divided through by 5 and I got this quadratic, okay? I got this quadratic. And so the solutions of this quadratic, again, I didn't bore you with going through the quadratic formula to do this, which is required. I don't think it doesn't factor nicely. You get irrational zeros. So here's the other two zeros we got. Of course, 7/5 is one of them, okay? And then also minus 7 minus 3 root 17 over 10, and then minus 7 plus. Now notice that this number right here, would be approximately negative 2, right? And I'm just saying that because look, the square root of 17 is 4, right? The square root of 16 is 4, okay? So minus 7 minus 12 would be minus 19, right? Okay, so this, but 17 is bigger, right? So this is approximately negative 2 right here, okay? Because you would have about negative 20 over 10 here, approximately, folks. Now, what about right here? In a similar fashion, you're going to get something around approximately 0.5. Now, how do we know that? Well, because, again, the very same kind of reasoning. Just think of the square root of 16 being here. This would be minus 7 plus 12, which is 5 over 10, which is about 0.5, right? It's a little bit more than that because it's the square root of 17, right? Okay, but we got a little bit of a concern here. There is a condition that we have to place on sine theta plus cosine theta. Remember, A is equal to sine theta plus cosine theta. Let me write this over here. A is equal to sine theta plus cosine theta. But there's a result that I proved in a previous video using Cauchy-Schwarz inequality. Now, a lot of people would prefer to use calculus. That's fine, but you don't have to. What we get here is this nice result. And again, I'm not going to show you. It's in, I think, one of the last videos I've done. But using Cauchy-Schwarz and the fact that sine squared plus cosine squared is equal to 1, you can get these bounds for this expression. Minus root 2 less than or equal to. And this is kind of a classical problem in a calculus textbook, but you do not need to take derivatives. You can just use Cauchy-Schwarz. All right. So, and I'll just go ahead and write A here, just in the name of time, okay, in the name of brevity. So we got this going on, right? Okay, so this is true. Again, I'm just stating this as a fact. You can use Cauchy-Schwarz to do it. Let me know if you can look it up. I think it's my next to the previous video or the one before. But in any event, notice that we would have to rule out this number right here, okay? This one is too big. Minus 2 is certainly less than minus root 2, right? So you'd have to rule this one out, but these other two guys are in range, right? 0.5 is definitely between minus root 2 and root 2. And also 7/5. Now, y'all, 7/5 is kind of close, but notice that 7/5 quantity squared, this is kind of nice here, is 49 over 50, right? Which is just a little shy of 2. Okay. Now, this is definitely less than 2, right? Just by a little bit. Okay, less than 2. And this should be squared right here, folks. So notice that when you take the square roots, the square root of 7 over 5, right up, this would all imply that 7 over 5 just barely meets the criterion, right? 7 over 5 is less than, this would kill the kids that love calculators, right? But again, we've showed just by doing squaring 7 over 5, you get 49 over 50, which is visibly less than 2. Take the square root of both sides and you get 7/5 is less than square root of 2. So you see we can, our two solutions are 7/5. I'll circle them. Okay, and then this guy right here is the other solution. Or I'll just, this is the exact answer right here, okay? These are the two solutions, ladies and gentlemen. And again, I hope you don't mind. I listed a few of the rational zeros and looked at it, you know, and noticed that 7/5 was the best try, and it worked out. If it, you know, you could have tried any of these others, but 7/5, given the size of these coefficients, looked like a good candidate. I was thinking it could have been 13 or 2. I didn't think it would be anything with 25 or 125 in the denominator, right? So again, folks, the answer, this is one of the answers right here, and this is the other answer. I like the problem quite a bit. Michael Penn called this a creative. He did one with the different constant. I think he did like 11 over 16 or something, but 90, just coming up with this constant is more challenging than the problem itself. But anyway, that is the end of the problem. Again, 7 over 5, and this guy right here are your two solutions.